So I'm going to talk about some ongoing work that I'm doing with my student, Tachapon Saranurak. It's on, the title will be a bit strange, but probably you will understand it in the end. So it's about emergency barriers for dynamic MST with worst case update time. So before I start anything, let me just get all this done at once, and this doesn't work. Okay, sorry. I'll just use my hand. So all the notations that I guess all of us probably are familiar with anyway. So MST is minimum spanning tree. ST is spanning tree. N is usually number of nodes in the graph. M number of edges. And in most of the talk, polylog N will be hidden most of the time, just because I'm lazy to write it down. And so when I say linear time, for example, it will mean near linear time. And the last thing that probably a little bit less usual is delta S. It will be the cut between S and V minus S. I will come back to this notation again when we need them. But otherwise, it's good to see them, all of them once. Now I have all notations, so I'll just start with the summary. So the motivation of the whole work is to work on this problem called worst case dynamic MST, minimum spanning tree. It's, to me, it's a pretty hard problem. So, and I guess people have a few questions about this problem. For example, can you do it in polylogarithmic time? And if you don't understand at this point, don't worry, I'll come back to everything. Can you do it a bit better than root n time? Or what techniques do you need to do this? Or can you prove a low bound? And I guess the last part is the most relevant part to the workshop. So unfortunately, there are a lot of barriers before we can actually solve this problem. So for example, worst case dynamic connectivity, worst case dynamic spanning tree, and so on. So the main barrier that I will look at, that I will focus on, and in this talk, is called emergency cut site oracle. And don't be surprised if you don't know about it, because it's recent, it's quite new. And the nice thing about this oracle is actually it's a barrier to quite a few other things. So one of them is this worst case dynamic spanning tree, which is a barrier to the MST itself. And the other problem is the minimum cut problem, the worst case dynamic minimum cut. So that's why I kind of like this barrier. And so the main point of the talk is what can we learn from this barrier? So just one thing that maybe I should warn you right now. So in the rest of the talk, it will be a positive result for algorithm people, which means it's negative for people proving low bounds. So, but it's algorithm talk. But there's a point of view of low bound provers too. So first of all, if you want to know whether you can solve the problem in polylogarithmic time for the dynamic MST or not, which I think is the big goal that we want to achieve, one message that I want to say is you better break this n to the 1/3 bound for this problem called emergency cut size first. And then on the other hand, if you want to prove low bound, maybe you can just look at this emergency cut size model and prove a low bound of n to the 1/3 in this model instead of going to the dynamic setting. And probably the weaker question is, can you actually just break this root n time? So it's kind of the base algorithm right now for dynamic MST. And the answer is maybe. But then if you really want to do it, from what we learned from here is that maybe you need to know this technique of flow techniques better in the dynamic setting. And the bad news is it's not really understood in the dynamic setting much. So probably we have to, if you really want to prove upper bound, maybe you have to understand this more. And again, if you don't understand anything I'm saying, hopefully I will try to make you understand in the rest of the talk. So the part one, I will just introduce the problem, dynamic MST, and the notion of worst case update time. So what is dynamic graph? So dynamic graph, probably most of you already know, you have this graph with n nodes. And the thing is, graph could change over time. So you start with this graph, and at some point, you probably delete some edge here. And you could add some edge later on. So edge could be added and deleted. And the goal, oh, yes, and then you probably delete some more. The goal is to maintain some information about the graph. So that's the general question. And okay, what do we want to actually maintain in this talk? So there will be three problems. So the first problem is called dynamic connectivity. And this is a simplified version of it. So what you want to know is whether the graph is connected or not. So you start from this graph, which is connected. So your algorithm should say that the graph is connected. And at some point, some edge got deleted, and then your algorithm should say that it's not connected anymore. And then it got connected again, so your algorithm should say that. A harder problem is spanning tree. So instead of just maintaining whether the graph is connected or not, you want to maintain the spanning tree or spanning forest. So you could start with this graph and with this spanning tree, the blue edges. And then you delete something, so the spanning tree has to change. And if you delete more, probably the spanning tree has to change again. So you have to keep maintaining this spanning tree. And the last one, which is the big boss that I am trying to attack, is minimum spanning tree. So now the graph has weight. You have weights on edges, like this one. And the goal is to maintain minimum spanning tree, which in this graph looks like this. So if you look at the weight, this is the smallest one. And then if you delete something, then you have to find a new spanning tree. And again, if you delete another edge, you have to find a spanning tree. So that's the three basic problems that we will talk about most of the time in this talk. So just to come back to the picture again, we have these three problems. Connectivity, which is, you can show that it's easiest. And you have dynamic spanning tree and dynamic MST, which is the hardest and kind of the main goal that we want to attack. The next thing is I have to define the notion of time complexity. So there will be two notions, amortized and worst case. So let me start with the worst case running time complexity. So it's just, the most simple thing that you can imagine of. You delete something, just one edge, and you want to know how much time you need to recover the information that you want to maintain. For example, if you want to maintain minimum spanning tree, it counts the time from when you delete this edge in this graph, and then until when you get the new edge, which is this edge, in the minimum spanning tree. So this is one time, and then you delete something again. You delete this guy, then you get this guy, and then you get another time t. And this is called worst case update time. And it's called worst case because we want to contrast it with something called amortized, which if you are not familiar with all this, just remember that it's easier to achieve. You don't really have to understand the notation. But if just a quick reminder, if you just want to know, is just say that you have amortized time t if after k updates, the time that you need in total is kt. So you just count from the beginning every time here. It's not like you start here. Okay, so what is known about this problem? Connectivity, spanning tree, and minimum spanning tree. So first, let's start with the easy case, amortized running time. And this is actually pretty much done a long time ago. What I mean by done is that you can have polylogarithmic amortized update time for all these three problems. And this is due to Monica Hensinger, Valerie King, and Mikko Torup, and a few others. So there's not much to do for amortized update time. How about worst case update time? So the situation is quite different. So one thing we know, which is pretty recent and pretty exciting, I think, is that the easiest guy, dynamic connectivity, again, worst case update time, now he's done. You can do it in polylogarithmic time, worst case, for this problem. And this is due to Valerie King and her co-authors a few years ago. And the main techniques that are pretty nice is this. One of them is sketching technique. So So how about other problems? So for other problems, actually the best algorithm goes back, I don't know, 30 years ago. It's due to Fredrickson and Epstein and a few others. So the running time is root n. So it works for MST, does it work for spanning tree and connectivity too? So that's still the best we know for this problem. So so this MST is basically what I want to try to say something about it. And so a few questions about this dynamic MST problem. One big problem is, can you get polylogarithmic time, which means that you probably solve the whole thing. And some people believe that it's possible because usually all these three questions go together. If you solve one, usually later on you manage to solve others. So probably it's possible. But right now, the even smaller question is, can you just break root n time of Fredrickson from 30 years ago? And it's not just for dynamic MST, but even for the spanning tree problem. And of course, if you want to break this, we have to know what techniques we need to solve the problem. And I guess one technique that probably we need is the sketching techniques, which were used for the connectivity problem by King, by Capron et al. And of course, can we prove low bounds instead if we don't think that this is possible? And in this talk, this is the main goal of the talk. I want to try to answer these questions by studying one barrier in this area, among many barriers. It is called the barrier in the setting called emergency. And we don't have a complete answer, but hopefully we have something. So the emergency setting that we will look at basically two problems. So one of them is emergency cut-size oracle, which is the main problem that we will look at. And the other one, which is a little bit easier, is emergency MST. So what is, now I'm sure many of you don't know what does it mean by emergency setting. So now I will talk about that a little bit. So first of all, let me introduce the notion of emergency setting. And the problem, I will use this emergency MST problem as an example. And by the way, the name of emergency came from paper by Badrascu and Mikhail Torup. It's called, I think in his paper it's called emergency planning, but I just want to make it shorter so it becomes emergency. And if you have written a paper about dynamic algorithms before, I think probably you have looked at this model before, but it's just that you didn't call it this way. So the main feature of the model is that you will have only one batch of updates instead of a sequence of updates. So to be more precise, so you will have three phases in the algorithm. The first phase, you just have a graph G, and you have to pre-process it. So you have this pre-processing, and then there is some updates. So you have some updates U to the graph, meaning you have this bunch of edge deletions and insertion. But the important thing is it's come in batch. So you see all the updates at the same time, not one by one. And then the last part, now you are asked some query, if there's any query, after the graph is changed. So here's an example. Emergency minimum spanning tree problem. So you're given this graph in the beginning, and then I just give you a batch of two updates, which is just two deletions, which I just say I will delete these two edges. And now your job is to find a new MST. So there's no query at this point. You just, once you see the updates, you have to recover the new MST as fast as possible. So I hope that is not too hard to see what it means. And probably now you probably ask why you have to look at this emergency setting. So I want to argue that it's important from both proving low bounds and upper bounds. So from proving upper bounds, so we will see this fact soon, that if you have fast dynamic algorithm, then you will have fast emergency algorithm too. And so emergency problem is kind of a problem that you have to break first before you can break really, the dynamic problem. And along the way, maybe you will learn some new techniques that you can use to really break the big boss. From the low-bound perspective, the emergency setting is, it's just 3 phases. It's closer to the static setting. So if you are hoping to use some conjectures that you have seen in the workshop before, like set or threesome or other problems in the static setting, probably it's easier to look at this model first because it just has a few phases. It's closer to the static setting. And this kind of low bounds was actually proven before in, I just give one example. So in Petrascu multi-phase problem, you just have 3 phases. And from there, he reduced from threesome to this multi-phase problem. So hopefully, if you don't have so many phases, maybe it's easier to reduce from the static problems. So so that's all the motivation. So again, I just want to make things more concrete. So let's look at emergency MST again. So we view it as a barrier to the dynamic MST problem. And why is it a barrier? And it is because the following fact. So if you want to obtain n to the root, root n to the 1/2 minus epsilon, worst case update time for dynamic MST, so something better than the current base upper bound, then you actually have to obtain the emergency MST algorithm with the following running time. So in the updates, you have a graph with m edges. The time that you need will have to be better than m root n, so m to the 1/2 minus epsilon. And in the update step, you have this list of update. Let's say you have U list. So the time that you need will have to be a little bit better than root n per one update in U. So it has to be U times n to the 1/2 minus epsilon.
Why can't you use an amortized algorithm for the emergency study?
Why can't you use the amortized algorithm? Because the amortized algorithm, so you already see the proof why you can prove this.
No, I don't know.
Okay. You cannot use amortized because amortized always starts from the beginning, when you count the running time. And we want to now emergency kind of separate the running time into 2 parts. And if you use amortized, this part usually will be blown up a lot. It will be threw up. Okay. But anyway, I will just give a short proof here anyway. So if you want to do this, you just pretend that the most important part is this update part. How can you handle updates? So you just pretend that you delete one edge at a time. So you have seen the example before where I start from this graph and I delete 2 edges here. So and then I get this new result. So instead of having 2 updates, you just imagine that you have one update in between, and then this update. And so to handle this update, you just run the dynamic algorithm. And then for another one, you run another dynamic algorithm, another update. And so you just need, update times the number of updates. And if you understand this part, you can see that you can replace this part, this running time with anything. So if I want to get polylogarithmic time for the MST, I have to get, almost basically linear time for preprocessing, and the size for the update has to be linear in the size of the updates. So you can replace by any number. So I would say that this is one of the obvious barrier for the dynamic MST if you have to solve this problem first, emergency MST. And I think it's a good time to mention another barrier, which is called emergency connectivity, just to put everything in the picture. So this actually was studied in 2007 by Petrascu and Torab. And so they kind of broke that already, but with some condition, but later on in the work of Capron et al., they kind of break it, I think, quite completely, except that the algorithm is randomized. So that obvious barrier is gone. And it's probably a good time to mention one minor result of ours as well. So the minor results say that for emergency MST, you can actually do things pretty fast. So in the preprocessing, you just need OM time. And in the update, you just need O of U time. So almost linear everywhere. And the technique is just, we just start from the sketching technique that Capron et al. Used, and then do some data structure called fully persistent. So it's not much. So, but that's a bad news I think for low-bound prover, because we want to have some barrier that we can say something. But now this guy is gone. So we need some new barrier, and I think the next kind of not very obvious, but the next natural barrier is this problem called emergency cut size oracle, which is going to be what I will focus on next. So what is emergency cut size oracle? So before I define emergency cut size oracle, I should define static cut size oracle first. So you just think of it as static data structure. So you just imagine you have two phases of algorithm. In the first phase, you have a graph G, and you can pre-process it. And then there's no change. You just get a query. A query is you have S as a parameter, and S is a set of nodes. And what you have to output is the size of delta S, which is the size of the cut. So it's defined here. Delta S is a set of edges between S and V minus S. And so this is the picture. So if I have this graph, if S is here, then I have to answer 4 because I have these 4 edges crossing between S and V minus S. So that's what we want to do for the static case. You want to quickly answer the number of edges between S and V minus S. Now, in the emergency setting, you just have one more step. So it's 3 phases now. So the additional step is you can update the graph with this update U. And so now you have a new graph G prime. And when you have a query S, you have to, again, output the size of the cut in this new graph G prime instead of the original graph. So that is the only difference. And this is an example again. So you have G, and then you probably delete some edges in G. So you get G prime. And when you query now, you have to answer 2 instead of 4. So this problem is pretty new, but it's not completely new. So actually, a few things are known. So first of all, we can get some approximation algorithm. And it's pretty fast. And this is, again, in the paper of Capron et al. That solved the connectivity problem. So they can pre-process the graph. Oh, and I should note that it actually works in the dynamic setting, not just emergency setting. So it can pre-process the graph in linear time and update the graph again in linear time in the number of updates. And then when you have the query, you can answer that with just size of the query, which you have to pay anyway. So these are the best running time you can get possible. The only problem is that it's approximation. How about exact algorithm? So I would say for approximation algorithm, this is pretty much done because you cannot improve this. How about exact algorithm? So you can show that actually there is a lower bound if you want to assume something. So the lower bound will be S plus the size of the output that you want to answer. So you should compare to this upper bound. So you cannot actually get this. You need this extra term, delta S. And this is for the query time, even for the static oracle actually. So, and even if you have a lot of pre-processing time, this still happen. You still need this lower bound. Okay, so we have lower bound that says that you cannot achieve exactly the same thing as exact algorithm. How about upper bound? And the problem is it's not known much, even for the static oracle. But the interesting thing is exactly here. So if you understand, my claim is that understanding exact algorithm for emergency cut size oracle is a barrier to worst case dynamic MST. So, and what I mean exactly is this. So here's the lemma. If you want to solve dynamic MST with this running time, n to the 1/2 minus epsilon, then we must obtain emergency cut size oracle with the following running time. So again, for the preprocessing, the best possible is linear time, OM. So, but now if you are talking about n to the 1/2 minus epsilon here, then you are allowed to have n to the 1/2 minus epsilon here. And also here for the update time. And for the query time, you are allowed to have this extra delta S times n to the 1/2 minus epsilon over here. So if you want to get something better than root n here, you better have this running time first for the emergency cut size oracle. And again, if you want to even go further to go to polylog n, then you have to improve all this to polylog n too. So I guess how much you can go here kind of tells you how far you can go with the dynamic MST problem. And okay, this is just a quick proof why this is the case, why the lemma is true. So right now you just want to solve the emergency cut size oracle. You start with a graph and you just give arbitrary weights to the graph. So let's say you start with this graph, you have these weights here. And then when we have update in the update phase, you just use dynamic MST to solve, to just maintain the MST. And so the thing that I want to explain that I think least trivial is how to get the query. Okay, so preprocessing and updates is pretty much trivial because you just run the MST algorithm. So how can you answer the query? So the first step is to explore all MST edges that is incident to S. So let's look at example here. So you have this graph. This comes from the first two phases. You already delete one edge, let's say here. This is the MST that you have, the blue edges. And now you have this query of S. You want to answer delta S. So the first thing you do is you look at all the edges incident to S, to nodes in S, which are this one, and this one. Three edges. And the next step is you delete edges that cross the cut, meaning these two edges. So you will end up with this picture where these two edges are deleted. And then you do the same thing again. So you get some replacement edge to get the new MST. So let's say these two red edges are in the MST. So this guy is in the cut again. So you delete him again. And so you have this graph. And at this point, you don't have anything left in the cut. So basically, the graph is disconnected. So at that point, you are ready to answer. And your answer will be the number of times you have deleted an edge, because you always delete edges that cross the cut. And that is 3 times in this example. So the running time should be, for the query time, should be obvious, I hope. So you probably need this much time to just read the query and also to explore edges inside S, which is in the MST. And then you have to do a few number of deletions, and for that you have to pay the time for the update time for the MST. But the deletion is your answer, delta S. So that's why the total query time will be S plus delta S times MST update time, which if you want to get better than root n, then this will be delta S times something better than root n. So with that lemma let me show you just this lemma one, right.
So for this, why did you need to have the minimum spanning tree rather than any spanning tree?
Good point. Any spanning tree will be fine too. I just want to focus on this. So that's why it's a barrier to spanning tree too. Only what you just have to be careful on one thing. It is that when there are different kinds of adversary, and these adversary that are deleting edges, they see the spanning tree before they make deletions. But you're right, spanning tree works too. Okay. So that's what I mean by being a barrier now. So if you want to get better than root n here, you have to get better than root n across all three parts here by the proof that I just showed. And another nice thing that I like about this barrier is that it's actually a barrier to, as I said before, dynamic spanning tree too. If you just do the same thing as before, using the same proof, you can show that this one works too. And you can use another question, which is a dynamic minimum cut problem to solve the problem. The parameter will be a bit different, but you can show that it's a barrier too. So that's all we want to answer. We want to know whether you can, how far you can go with this. Can you replace this red thing by polylog, for example? And our result is kind of something in the middle. It's break what we asked a little bit, but not all the way through polylog. So we show that there is an emergency cut size oracle such that the preprocessing takes this n to the 1/2 plus little o1 time. And little o1 high is kind of is written here, log divided by square root log. And update time, again, you have this extra n to the 1/3 plus little o1. And also for the query time, you have n to the 1/3 plus little o1. And there are some side results as well. So first of all, as I said, even the static setting is not, so far, we are not aware of anyone saying about anything about static oracle. So what we found is you can get everything, the best possible for a static case. So OM time for preprocessing, OU time for update time, and this S plus delta S for query. And it's actually an important component to solve the problem in the emergency problem as well. And actually, I have to note one thing. So actually, we can output delta S too, not just the size of the delta S. So in the end, and because we have the low bound anyway, that you need this much time. So
should be an update, right?
Which one?
Static. There's no update.
Oh, sorry. You're right. Forget about this. For static setting, there's no update. It's a typo. Yes, and we can output delta S too. And later on, I actually will kind of emphasize this fact. We actually need to list all the edges crossing the cut. And sometimes I will call this emergency cut set instead of emergency cut size. It's just to say that you can actually output edges in the cut. And as I said before, it is a barrier to the mean cut problem too. And you need different parameters for that, but we can break that one too. But it's not a focus of this talk. So I have stated the main results. And I think people will interpret it in different ways. So I will just say how I interpret it, as I said in the beginning. So the first question you probably ask is, can you get polylog time for dynamic MST problem in the worst case? And so for me, I think since we have this n to the 1/3 right now, so my reaction will be, you better break this n to the 1/3 bound for the emergency cut size first before you can get polylog n for MST. And if you want to prove low bound instead, if you want to say that this is not possible, probably you can show n to the 1/3 lower bound in this model for this problem. And again, I think it's probably easier because it's closer to the static setting. The other probably less ambitious question is try to just break the current base bound, which is root n. And my reaction would be probably, maybe, but then I would guess that you probably have to understand the flow techniques better in the dynamic setting. And why do I say this? The reason is the way we solve the problem. So now I will show you a little bit of how we kind of approach the problem. So this is our oracle in the end. And to go here, you just derive quite a few flow techniques. Up here is the max flow, approximate max flow, which we have seen progress in the last few years. And then you use that with some cut matching games to get some sparsest cut algorithm, a variant of sparsest cut called balanced sparsest cut. And from there, we developed something called high expansion decomposition. And on the other route, we have this three-cut sparsifier, which were developed, again, recently by Recke and his co-authors. And from there, we get this static cut size oracle. And static cut size oracle is part of our emergency oracle. It's one of the important subroutine. And of course, you need these linear sketches, which were used in previous paper by Capron et al. For the dynamic connectivity problem. So my interpretation here is if you want to make this one, or getting something about dynamic case, probably you have to understand better how all these play a role in the dynamic setting. Or otherwise, you have to find some other way to solve the emergency cut size problem. So, my goal, I think I have about 10 minutes left. So the goal right now is just to give you kind of a sketch of what's happening in this picture. And that's, 5. Okay, thanks, fine. Okay, anyway, yes, so it's going to be a sketch of the algorithm. And again, as I said before, our algorithm actually output the cut. So don't be confused if you see that we are actually output the cut. And I guess I will just have time to explain this part. And again, very roughly. So I will just make things a bit simpler and assume something. So I will assume that we will have exactly n deletions and no insertions during the update. So you have a graph, and then you make n updates, which is deletions. And then you do something. You do the query. So we will have basically two cases. The easy case, which I'm not going to go into detail so much, is when the query size is less than n to the 2/3. In this case, it's easy because you can just use previous techniques that we know before, which is some sketches and some random partitioning technique. So it's pretty simple. So I'm going to skip the details here. So, and the main focus will be how to deal with this hard case when the query is pretty large. And for here, we need something called high expansion decomposition. So what is high expansion decomposition? I have to define something first. So if you have a set of a node, then expansion of the set of the node, which is denoted by Cs, will be the size of the cut, from S to S bar, divided by minimum between S and B minus S. So if you imagine that S is smaller than n divided by 2, then it's just the number of edges divided by the number of nodes. And the expansion of the graph is just the minimum of that. So minimum among all the S in the graph and phi of that. Okay? So that's the usual definition. Oh, and this is example. So it's 3 here and it's 2 here. So now what is high expansion decomposition? It states the following. You given a parameter alpha, and we can do the following in almost linear time. So the running time that you have is m plus 1 to the little o1. So you can partition the edges in G into 2 parts, h0. So the part 1 is h0, and the other part will have this h1, h2, and so on. So in h0, the nice thing about h0 is it's sparse. So you have these many edges, alpha times n to 1 plus little o1. Again, alpha is parameter that you have. And for the rest, you will have high expansion. So the expansion will be at least alpha. Okay. Yes?
High expansion on the set of nodes in which they're adjacent, or assuming they're not necessarily going to...
So expansion by this definition. So for every set of nodes, it's that. Oh, It's just in that graph. You're talking about this subgraph HI.
Yeah. So HI might only contain a subset of the nodes as well, or?
Right, it might contain subset of the nodes and subset of edges. Right, yes. Okay, and okay, we will need this just in the beginning. In the pre-processing, you just run this expansion decomposition. And then to add, in the rest, you just handle all these H0, H1, H2, and so on separately. So how can you handle the sparse part, the H0? You just run the static algorithm. In the pre-processing, you do nothing for this H0. And because the graph is sparse, when there are deletions, you just run static algorithm. And you don't have so many edges there, so you will be fine. And then when you have query, you just use this static algorithm to answer the query. So let's, I will go a bit quickly now. So now for each high expansion HI, what do you do? So there is this easy case where you have this subgraph H which has high expansion, and this is the query. If the intersection is not so large, then you can just use the easy case that we had before, that the query is small. Then you just run these sketches that we had in the previous part that I said that easy. So the interesting part is this part, when the intersection is high. But then when the intersection is high, then we know that the answer will be large because the graph has high expansion. So we know that this delta HI and intersection between this is at least 2n. And since we delete only n edges, so we will have a lot of edges left that we should output. So what we will do is, again, we use static oracle in the pre-processing. And during update, we do nothing. And then for query, we just use this oracle to answer the query. Okay? So of course, the oracle might output some deleted edges that you already deleted, but it's not much. You have n deletions, but you have answer of 2n. So that's a lot to answer. And so you can charge the cost to your answer. So there's some more details, but I think I will skip that. And I will just show you the picture that I showed in the beginning again. So the whole talk is about this guy, emergency cut size oracle. And again, it depends on what you interpret, but I would say that it's an interesting object that we should study first if we want to attack dynamic minimum spanning tree. It depends on whether you want to prove low bound or upper bound, but I think it's interesting from both point of view. So, and just a few open problems. So, can you prove low bound for this problem, for example? And that will be great, because if you can prove some low bound here, you will rule out the possibility to get dynamic spanning tree and MST, and also min cut at the same time. Or if you can prove upper bound, improve what we had from n to the 1/3 to polylog n. And I think, and can you extend the result to dynamic setting? Okay, so thank you.
Any questions?
So your algorithm is quite involved, right?
There are many cases, and the part that is hidden is this high expansion decomposition as well.
But do you think, I'm sure you tried hard to simplify it. Is your...
Oh yeah, this is already simplified, but...
But is your feeling it has to be so complicated? Do you have any intuition why?
I think this decomposition part is the most complicated part, and I think it has to be there. That's my belief. So, but probably other parts that you need case analysis, probably you can avoid. But it's not clear. If you probably can do something better for this, if you know better how to use this high expansion decomposition, I would guess that probably you can avoid something other parts. Right now, it's just that we have limited way to use it. So.
Any other questions?